Hello and welcome students. In today's lecture, we are going to see scalar triple product. Now, when I say scalar triple product, see, first of all, the word triple. Triple stands for 3. So we are going to have product of 3 vectors. We are going to have product of 3 vectors. That is why it is known as triple product. Now, when I say product of 3 vectors, remember, the final outcome that I must have should be a scalar. When I will multiply the 3 vectors, I will get the product of 3 vectors. That is why it is known as triple product. But the final product which I should get, what should it be? It should be a scalar. It should be a scalar. That is why we call this as scalar triple product. For example, if I have A bar, B bar, and C bar as 3 vectors, I have A bar, B bar, and C bar as 3 vectors. I need to multiply these 3 vectors in such a way, I need to multiply them in such a way that finally I should get a scalar. So I will call this as a scalar triple product. Now students, as you know that 2 vectors can be multiplied with each other to give you a scalar. We call that as scalar product of 2 vectors, that is dot product of 2 vectors. This is dot product of 2 vectors. You know you can also multiply 2 vectors in a way to give you a vector. So that you call as the vector product of 2 vectors or cross product of 2 vectors. So as in case of product of 2 vectors, we can get a scalar and we can get a vector. Similarly, in case of product of 3 vectors, we can get a scalar. We can even get a vector. Yes. You can even get a vector. Even in case of product of 3 vectors, you can get a scalar, you can get a vector. Now, when you multiply 3 vectors in a way to get a scalar, you call that as scalar triple product. And when you multiply 3 vectors in a way to get a vector finally, you call that as vector product of 3 vectors. You will call that as vector product of 3 vectors. So here you have scalar triple product, and if you are getting the final outcome as vector, you will call that as vector triple product. What will you call it as? Vector triple product. So let us now start with scalar triple product. We will begin with scalar triple product. Let's have the definition here. Scalar triple product of 3 vectors A bar, B bar, and C bar is defined as A bar dot B bar cross C bar. Scalar triple product of 3 vectors A bar, B bar, and C bar is defined as A bar dot B bar cross C bar. So there are a few things that you have to understand. See, here you wrote A bar, B bar, and C bar. And here you are writing A bar dot B bar cross C bar. So is it the reason that since we have A bar, B bar, C bar, we are writing A bar dot B bar cross C bar? Yes, that is true. Is this order A bar, B bar, C bar responsible for you writing A bar dot B bar cross C bar? Yes, that is true. When you say the scalar triple product of A bar, B bar and C bar, you will write A bar dot B bar cross C bar. And if you are saying the scalar triple product of A bar, C bar and B bar, that and is okay. That and is okay. Even if you're not writing and, it is fine. If you're saying that scalar triple product of A bar, C bar, B bar, then remember students, this you will write it as A bar dot C bar cross B bar. So remember, the order is important. The order is important. This is first thing. So how did I define? I said scalar triple product of three vectors A bar, B bar and C bar is defined as A bar dot B bar cross C bar. And here I told you that order is important. Order is important. If you have B bar, A bar, C bar, then how would you write? Then this you will write it as B bar dot A bar cross C bar. You will write this as B bar dot A bar cross C bar. This is the way you will write. Okay, fine. So this is one thing which one has to note in the definition, that order of these three vectors is important. So you may write here, note the order of three vectors is important. One more thing. Here I have written A bar dot B bar cross C bar. In some books, most of the books rather, you will notice that B bar cross C bar, it is put in a bracket. It is put in a bracket. So you will notice that scalar triple product of A bar, B bar and C bar, A bar, B bar and C bar, it is written this way, where B bar cross C bar is put inside a bracket. Okay, that is, it is the cross product of B bar and C bar which you have to get first. What does it mean? It means that you have to get the cross product of B bar and C bar first, which will get you a vector. As you know, students, that when you get the cross product of B bar, C bar, you will get a vector. And that vector which you get, remember, this vector which you get, you will get the dot product of this vector with A bar. This vector with A bar. That is what it means. This is what it means. B bar cross C bar, you have to evaluate first. Once B bar cross C bar has been evaluated, it will give you a vector. That vector you have to take a dot with A bar. That vector you have to take a dot with A bar. So you will find somewhere in some books that it is put inside a bracket. But here I have a question. The question is the bracket necessary? Is the bracket necessary? That is, is there a chance of I not putting a bracket and then committing a mistake? See, what way is the bracket helping me? The bracket is indicating that we need to first find the cross product of B bar and C bar. What is the bracket indicating? It is helping us to know that we have to first get this, and then whatever vector we get the dot with A bar. But I have a question. In case if I don't put a bracket, do I stand a chance to commit a mistake? The answer is no. The answer is no. Even if I don't put a bracket, try to understand, students, that even if I do not put a bracket, see, even if I do not put a bracket, say it is A bar dot B bar cross C bar. I'm not putting a bracket. So is there a chance that I go for this first? Is there a chance that I go for this first? See, if I'm going for this first, just understand what will happen. If you go for dot product first, a bar dot b bar, this will give you a scalar. You know, this is scalar product of two vectors. And students, you know that if you get the scalar product of two vectors, you will get a scalar. So a bar dot b bar is a scalar. It is a scalar. It is a scalar. It's a number. It's a number. It is not a vector. It is just a number. Now tell me, students, can we have cross product of a number? See, here you have cross product. So can we have cross product of a number with a vector? Can we have cross product of scalar and a vector? That is not possible. Whenever you say cross product, remember cross product has to be between two vectors. If you are saying cross product, see, if you are saying cross product, it has to be vector here and vector here. If you are saying cross product, it has to be vector here and vector here. But what is happening? A bar dot b bar is a scalar. So you cannot have cross product of a vector with a scalar. So I understand that this way, if I consider, I'm going to get a wrong result. So even if the bracket is not there, it is understood that it is first b bar cross c bar. Then whatever you get, you will go with a bar. But on safer side, if you are putting a bracket, there is no harm to it. So remember, students, if you see somewhere like a bar dot b bar bracket cross c bar, straightway you should understand this is wrong. It is not correct. It has no meaning. You should understand that this has no meaning. It is no meaning. Absurd it is. I hope you all followed this. The scalar triple product, of a bar, b bar, c bar is denoted by, you write it in a box, a bar, b bar, c bar. You write this in a box like this, okay? It is denoted by, in a box, a bar, b bar, and c bar. Now, because of this box, we also call scalar triple product as a box product of three vectors, okay? Scalar triple product of three vectors need not be written, three vectors, it is understood. Scalar triple product is also known as, box product. So therefore, what we can say? We can say box product a bar, b bar, c bar. Please don't put a comma. Box product a bar, b bar, c bar is equal to a bar dot b bar cross c bar. We will write box of a bar, b bar, c bar as a bar dot b bar cross c bar. This is how you will write. So this is the definition of box product of, scalar triple product of three vectors a bar, b bar, c bar, or box product of three vectors a bar, b bar, c bar. Now, if a bar as a1 I cap plus a2 j cap plus a3 k cap B bar is B1 I cap plus B2 J cap plus B3 K cap. C bar is C1 I cap plus C2 J cap plus C3 K cap. Then how do I write A bar, B bar, C bar? Then how do I write the box product A bar, B bar, C bar? See, now I will go for the derivation. Okay, this is a part to be discussed, understood. So now you know, students, the box product A bar, B bar, C bar is A bar dot B bar cross C bar. Okay, let me write this as 1. What I do is, I will first find out B bar cross C bar. I will first find out B bar cross C bar. Now you know B bar cross C bar is determinant I cap, J cap, K cap. What is B bar? B1, B2, B3, C1, C2, C3. This is B bar cross C bar? Yes. That is, I will get I cap, B2, C3 minus C2, B3 minus J cap, I will get B1, C3 minus C1, B3 plus K cap, I get B1, C2 minus C1, B2. This is B bar cross C bar. Okay, this is B bar cross C bar. Fine. Now in this, I want to make a small change. Change means that is about the order. See, this I cap which I have here, can I write it here? Definitely yes. Why not? You can always write I cap there. So if you are writing it here, what you will do, you will remove this. This J cap which I have here, can I write the J cap after the bracket? Definitely yes. So this J cap you will remove from here. And this K cap which you have, I would write this as here, K cap. Okay. So this is my B bar cross C bar. This is vector B bar cross C bar. I write this as number 2. Now it is time I calculated, I found A bar dot B bar cross C bar. What I'm saying, I find now, see, I got B bar cross C bar. Now I go for A bar dot with B bar cross C bar. So see, what do I get? I'll write here, therefore, A bar dot B bar cross C bar will be, you know, what is A bar? A bar is A1 I cap plus A2 J cap plus A3 K cap dot B bar cross C bar. What is B bar cross C bar? B bar cross C bar is B2 C3 minus C2 B3 I cap minus B1 C3 minus C1 B3 J cap plus B1 C2 minus C1 B2 K cap. So here I have dot product of two vectors. You have dot product of two vectors. One vector is here, the other vector is here. You know, when you take the dot product, what you do? You will multiply the coefficient of I cap with the coefficient of I cap. You multiply the coefficient of J cap with coefficient of j cap, you multiply coefficient of k cap with the coefficient of k cap, and then you add those respective products. We have already done. If I ask you what is a bar dot b bar, if I ask you what is a bar dot b bar, wouldn't you say a1 b1 plus a2 b2 plus a3 b3? Yes, that is what it is. You multiply the coefficients of corresponding coefficients and then you add the product, respective products, right? So here, students, see what do I get? So what I will do is I will multiply. So a bar, I will get here a bar dot b bar cross c bar. I will get c a1 into this. I will get here b2 c3 minus c2 b3 a1. Okay, this into a1 minus b1 c3 minus c1 b3 a2 plus b1 c2 minus c1 b2 a3 a3. Now I have a question for you. Okay, let this be number 3. I have a question for you. Can I replace this b bar cross c bar? Can I replace this b bar cross c bar by this? Obviously yes. Why? Because this is also b bar cross c bar. So here, see, I have here a determinant I cap, j cap, k cap, b1, b2, b3, c1, c2, c3. What do I have here? I have a determinant whose value is equal to this, So students, if this thing, try to get this, if this thing on the right hand side which you have of equation 2, this thing which is on the right hand side of equation 2 is equal to this determinant, I'm sure you will understand that this thing is equal to, this thing on the right hand side is equal to a determinant, it is equal to a determinant a1, a2, a3, b1, b2, b3, c1, c2, c3. What is this? It is nothing but this determinant. It is nothing but this determinant. You can check. If you evaluate, you all have already learned how to evaluate a determinant. You all have already learned how to evaluate a determinant in lower standard, that is 11th standard. So tell me, students, if I evaluate this determinant, if I ask you to expand this determinant, won't this give you the same thing here on the right hand side? Yes. So now you have a new formula. You have a formula for the scalar triple product. A bar dot b bar cross c bar is determinant a1, a2, a3, b1, b2, b3, c1, c2, c3. Okay, you can also write the same thing using the other definition, using the other symbol. Using the other symbol, you can write the same thing. What is the other symbol? You write it in a box. So here you will write box of a bar, b bar, c bar. Box of a bar, b bar, c bar is equal to, what is it equal to? A1, A2, A3, B1, B2, B3, C1, C2, C3. This is it. You can copy this also. Now, you have to commit to memory that box product of A bar, B bar, C bar is A bar dot B bar cross C bar. And then you have to know that this is equal to A1, A2, A3, B1, B2, B3, C1, C2, C3. So it is my suggestion to you that you have to know it in this order. I tell you why I'm stressing, because many students, it has been found that they know that box of A bar, B bar, C bar is this. But this part they neglect. Please don't do that. Don't do that. You should know that box product A bar, B bar, C bar is A bar dot B bar cross C bar. And then it is equal to this. Let me write this as 1. Okay. So if I write here A bar, C bar, B bar, A bar, C bar, B bar, then what will it be? It will be A bar dot C bar cross B bar. Perfect. And what will that be equal to? That will be equal to A1, A2, A3. And here you will interchange the rows. C1, C2, C3, B1, B2, B3. You are interchanging the rows, right? Now C bar cross B bar it is. So C bar coefficients will come in the second row. So this is number 2. I have a question. Are these two determinant related anyways? Look at these two determinant and think, are they related anyways? Yes. Yes. We have done in the properties of determinant that for a determinant, when any two rows are interchanged, the value of the determinant will change its sign. The value of the determinant will change its sign. It means if this determinant had the value, say alpha, then this determinant will have the value negative alpha. It will have the value negative alpha. These two determinants are negative of each other. They are negative of each other. So what I understand is, that these two determinants are negative of each other. So in the next step, what I can write it is equal to, see, in the next step I am writing, this is equal to negative of upper determinant A1, A2, A3, B1, B2, B3, C1, C2, C3. What I wrote, I'm writing that this determinant is negative of this determinant. This determinant is equal to negative of this determinant. Okay? Yes. Suppose what I said, suppose this has value alpha and this has value minus alpha. So how will I equate minus alpha to alpha? How will I equate if I want to write equal to sign between them? What will I do? I will write minus alpha is equal to minus of alpha. The same thing I have written. What I have written? I have written this determinant is negative of upper determinant. So now this gets me negative of, what is this? What is this determinant? It is A bar, B bar, and C bar. And what did I had here? I had here box product A bar, C bar, B bar. So now I have a very important property of box product. What is the property? The property is whenever you interchange any two vectors in a box product, then the box product will change the sign. The box product will change the sign. See, A bar, C bar, B bar, what you did, you interchange these two vectors. You made it A bar, B bar, C bar. So what you got? You got negative. So whenever there is an interchange of two vectors, whenever there is an interchange of two vectors, the box product will change the sign. The box product will change the sign. So I can write here property number 1. Any two vectors in scalar the sign. It changes the sign. Okay. I can give you a few more examples. For example, if I have A bar, B bar, C bar. Okay. And here now what I'm doing, see, I'm interchanging these two. I'm interchanging A bar with C bar. Okay. And I write C bar, B bar, A bar. Will they be equal? No, they are not equal. They are negative of each other. So if you write a negative sign, now they are equal. Now they are equal. See, if I have A bar, C bar, B bar, okay? And what I do is I interchange A bar with B bar now. I interchange A bar with B bar. So I have B bar, C bar, A bar. Okay, look at these two only. Look at them. Look at only these two. Don't see other box products. You have A bar, C bar, B bar, and here you have B bar, C bar, A bar. So what you are doing? Are you not changing A bar, interchanging the position of A bar and B bar? Yes. So this will be negative of this. I hope you all followed it. Please copy. So as I taught you just now, it was about the interchange of any two vectors in a scalar triple product. You saw if you are interchanging any two rows, I'm sorry, when you are interchanging any two vectors in a scalar triple product, the value will change its sign. So if I write A bar, C bar, B bar, what are you doing? You are interchanging these two. So you change the sign. So here, in order to make them equal, you will have to put a negative sign. Now they are equal. As such, they are not equal. They are not equal. Why? Because this is negative of this. I repeat this again and again, again and again. Remember, this one is negative of this. In order to make them equal, now you put a negative sign. So now they are equal. Okay. After this, I want you to consider not the interchange between two vectors, but a cyclic change of vectors. See, try to follow the word, or cyclic change of vectors. Now, what do I mean by a cyclic change of vectors? See, when we say a cyclic change, actually, we are trying to have an idea where if I have, suppose if I have here 3 places now, and in these 3 places, if I have suppose I have cross here, I have a circle here and a star here. Okay, now see, the interchange is, if you are just interchanging any two of the objects, you know, it will be like you put a star, if you put a circle here and a cross here. Okay, so that is known as interchange. That is known as interchange. What you do, you put the cross here and the circle here, then that is interchange. I'm not going for interchange. What I'm going for is the cyclic change. Okay, so cyclic change, see how will it happen? Cyclic change. What will happen is the star comes to the place where the cross is there. The star will come to the place where you have crossed. So the moment star moves out from here, see the moment star moves out for this from this position, okay, the circle will take this position. Now when circle is moving out to take the position of star, the cross moves to the circle position. So how does it look now? It look like this. See, here you get the circle, here you get the star, and now here you have the cross. This is known as cyclic change. It is known as the change of the objects in cyclic order, or simply the cyclic change of the objects. See, this is not interchange of any two. It is here when you are interchanging any two, what happens is one out of the three remains at its original position. See, if I interchange circle with cross, the star will remain where it is. If I interchange star with circle, then cross will remain where it is. But when I'm going for a cyclic change, you notice that all of them have changed their position. You notice that all of them have changed their position. Okay. Now the cyclic change can be both the ways. Here we went for the cyclic change. And that was in which order? That was in anti-clockwise order. But you can also go for cyclic change in clockwise order. See, you can go for cyclic change like this. See, this way also it can happen. So if you're going for the cyclic change in clockwise, see, you have this place, and this place. Now see, the star will move to the circle's place. Okay. Now the star place is vacant, so cross will move here, and now the cross place is vacant, so the circle will move to the cross place. See, this is, and what is it? It is the cyclic change in clockwise order. It is the cyclic change in clockwise order. So such a change, if you have, you call it as a cyclic change. Now why did I teach you? See students, in the scalar triple product, I'm going to now incorporate this kind of change. So here, see, I have A bar, B bar, and C bar, right? So I'm not going to interchange two vectors. I'm going for a cyclic change. So see, when I go for a cyclic change, how is this going to happen? This B bar moves to the place of C bar. Now, when B bar moves to the place of C bar, what happens is it is because C bar has moved out and it is going for the place of A bar. You see this? C bar is moving out for the place of A bar. Okay, C bar is moving out for the place of A bar. Now, as C bar moves out, the place of C bar is vacant. So B bar is moved to the C bar. And as B bar now is on the move, B bar place is vacant, A bar moves here. And the moment A bar is out of its place, C bar occupies that. So it is C bar, A bar, and B bar. C bar, A bar, and B bar. B bar comes here, C bar there, and A bar. This is cyclic change. Now, when there is a cyclic change, this is cyclic change. And when there is a cyclic change, remember students, the scalar triple product that you get, its value remains the same. The scalar triple product that you get after the cyclic change, the value will remain same. That is, once again, the cyclic change. C bar moves and it goes to the place of A bar. When C bar is on the move, the place of C bar is vacant, B bar takes its place. And when the B bar is on the move to C bar, B bar place is vacant and A bar will come here. See, this is cyclic change, the change in cyclic order. So how do you have here? You have C bar, A bar, and B bar. Now here you will notice that each one of them have changed their position. You will notice that each one of them have changed their position. This is not interchange of two vectors. Now I wanted to tell you that these two have the same value. Okay, how do I say, okay, how do I say that these two are equal? I wanted to prove that. How do I say that these two are equal? So unless I prove it, I will not write it. Let us go for this. See students, you know that A bar, B bar, C bar. How do you write A bar, B bar, C bar? You write A bar, B bar, C bar as A1, A2, A3, B1, B2, B3, and C1, C2, C3. This is what you write? Yes. Now, when I interchange the two rows, that is R2 and R3. So what will happen? When I interchange the two rows R2 and R3, what will happen? I will get, see right now, this is equal to this. Okay, this has the value equal to this determinant. This is equal sign, equal to sign. Now the next one which I get, see the next one which I get here, what happens is, I'm writing here C1, C2, C3, B1, B2, B3, and in the first row A1, A2, A3. Now I know that the determinant which I now got is a negative of the previous determinant. So this value is negative of this value. So in order to have equality, I'll have to put a negative sign. Now they are equal. Now they are equal. Okay, fine. Now the next what I do is, see, let me focus on this determinant only. Okay, I want you all to focus on this determinant only. What I mean is, for time being, just ignore that negative sign. This negative sign you ignore, just focus on this determinant, this determinant. So in this determinant now, I'm going to change R1 with R2. Let me interchange R1 with R2. So when I interchange R1 with R2, see, I will get here C1, C2, C3, A1, A2, A3, R1 and R2 are interchanged, B1, B2, B3, B1, B2, B3. Okay. See, I'm talking about the determinant which I enclosed in this box. For that determinant, I interchange R1 with R2. Now, is this determinant equal to this determinant? The answer is no. Why? Because you know, if the two rows are interchanged, the value will be negative. So what I will do, I will put a negative sign. I will put a negative sign here. And why this negative sign? Now, after putting negative sign, I can say that the determinant you have out here, it is equal to this thing. It is equal to this thing. Okay. So for this determinant, I have written a new determinant with a negative sign. Now I will go for this negative sign. So with the consideration of that negative sign, minus of minus, try to understand students. Now this determinant which you have here, it is equal to this determinant in the box. Now both the determinant in this box and determinant in this box are equal. They are equal. Okay. But I haven't put an equal to sign in between. See, there is no equal to sign here. I'm not putting an equal to sign. Why? That I cannot do unless I consider this negative sign. Okay, so when I consider that negative sign, what will happen? This will become positive. Minus of minus will become positive. Minus of minus will become positive. See, minus of minus. So this is whole thing, and the negative sign once again. Now it is equal. Now see, minus of minus become positive. And finally, what you get is, students, see, this is equal to, you get it here equal to you get it here equal to C1, C2, C3, A1, A2, A3, B1, B2, B3. Okay, so you started from here. See, you had A bar, B bar, C bar, which was equal to this, which was equal to this, and finally this. But what is this equal to? It is nothing but C bar, A bar, B bar. You can check. You can check. It is nothing but C bar, A bar, and B bar. So here I establish the relation. Here I establish the relation that when there is the cyclic change of vectors, when there is the change in vectors in cyclic order, then the value of scalar triple product remains same. You have A bar, B bar, C bar. You changed this vectors in cyclic order. So the value will remain same. These two are equal. I'll give you one more example. Say here, I have here A bar, B bar, and C bar, right? This time I go for the cyclic change in which direction? In clockwise. So see here, the cyclic change like this. Okay, so now C bar is on the move to go to A bar. When C bar will have changed, when C bar will have left its place, B bar has a chance to come here, and then A bar will come here because B bar will also be on the move. So what you will have here is, see, you have here C bar is on the move, so B bar comes here, A bar comes here, and C bar. Okay. Now let's go for one more cyclic order change. So see here, I go for a cyclic order change once again. So what will happen now? B bar is on the move. So A bar comes here and C bar will come here. You see this? This is cyclic order change. So you will have here, see B bar here, then C bar and A bar. See, they are equal. So this is equal to this. See, they are all equal. Why? Because every time I'm changing in the cyclic order. Now, once again, I go for a cyclic order change. Let's go for this time anti-clockwise. So A bar is on the move. A bar will come here. So C bar will go there and B bar will go there. What will this get you? This will get you, see, A bar, B bar, and C bar. So from where you started, you have reached the same place. You see this? From where you started, you have reached the same place. So this is, now I will write the property here. I will write whenever there is change of vectors, of scalar triple product in a cyclic order, whenever, I'm sorry, there, whenever there is a change of vectors of scalar triple product in cyclic order, the value of scalar triple product, does not change. The value of scalar triple product does not change. This is property number 2 of scalar triple product. Now we go for property number 3. See, the scalar triple product of 3 vectors A bar, B bar, C bar is equal to 0, equal to 0 in following cases. In following cases, equal to 0 in following cases. So let's do it first. See here. The first one is when any two vectors are collinear with each other, collinear to each other or collinear with each other. If any two vectors are collinear with each other, what will happen? The scalar triple product will be equal to 0. So for example here, think B bar and C bar are collinear. Okay, just for the sake of understanding, I'm taking B bar and C bar to be collinear. See, so what will happen? A bar dot B bar cross C bar. This is your scalar triple product. This is your scalar triple product, right? Now see, if you have the two vectors B bar and C bar collinear, what will be the angle between B bar and C bar? The angle between them will be either 0 or 180 degree. If they are collinear and in the same direction, then B bar and C bar will be having angle between them 0. Or else, if they are collinear and in the opposite direction, if you have B bar and C bar collinear and in the same direction, then the angle between them, what you will have? You will have angle between these two vectors as 0. But suppose you have B bar and C bar collinear but in opposite direction. This is B bar and here you have C bar. Now when you have them in opposite direction, what is the angle? The angle is 180 degree and here the angle is 0 degree. But remember students, in either cases, 0 degree or 180 degree, what will happen? Sine of these two angles is equal to 0. And how do you define cross product? The cross product we will define is mod of B bar mod of C bar, sine of angle between them times the unit vector which is in the direction perpendicular to B bar and C bar. So sine of 180 degree or sine of 0 degree is 0. Now since sine of this part, that is sine of that 180 degree or 0 is 0. If this part is 0, 0 into any number is 0 and 0 into n cap is 0 bar. So what you have here? You will have here A bar dot 0 bar and A bar dot 0 bar is equal to 0. So remember student, if any two vectors are collinear, you will get the answer as 0. You will get the answer as 0. If any two vectors are collinear in a scalar triple product. Now you have another case. Suppose if A bar and B bar are collinear. This is the case when B bar C bar are collinear, so the cross product is 0. Now there is a case, suppose you have A bar collinear with B bar, then what will happen? If you have A bar collinear with B bar, suppose you have A bar and B bar are collinear. Now you don't have the cross product between them. So see here, it is A bar, B bar, C bar. So that is equal to A bar dot B bar cross C bar. Now you cannot say that cross product is coming 0. Cross product is not going to come 0 because B bar and C bar are not collinear. It is A bar collinear with B bar and C bar. No worries, no worries. See here, suppose I have B bar here and C bar here. See, this is how I have B bar and C bar. I have B bar and C bar like this. Okay, they are not collinear. This is vector B bar, this is vector C bar. They are not collinear. B bar and C bar, they are not collinear to each other. Yes, A bar is collinear to B bar. So I will have A bar which is collinear to B bar. So think A bar and B bar are collinear and they are in one direction. They are in one direction. This is how they are. Okay, this is A bar. They are in one direction. The only thing is A bar is bigger than B bar. You see this? Now you understand that smaller vector is B bar and the bigger vector is A bar. What are we going to find? First, we'll find B bar cross C bar. That is, I'm finding, try to understand students, I'm finding B bar cross C bar. I will begin with here. I will begin from here. See, B bar cross C bar. Okay, you know, I will start from B bar. I will keep the four fingers of my right hand in the direction of B bar, and then I will bend them towards C bar. Now the direction of thumb will get me the direction of B bar cross C bar. The direction of thumb. So see, B bar cross C bar will come this way. This is B bar cross C bar. Okay. Yes, this is B bar cross C bar. Now check this out. This is B bar cross C bar. This B bar cross C bar is perpendicular to B bar as well as C bar. Yes. Now, since B bar cross C bar is perpendicular to B bar and you had A bar collinear to B bar, what will happen? B bar cross C bar is also perpendicular to A bar. B bar cross C bar is also perpendicular to A bar. So the angle between B bar cross C bar and A bar is 90 degree. Now here you have A bar dot B bar cross C bar. You know, the dot product of two vectors which have angle between them as 90 degree is equal to 0. Why? Because how do you define dot product? It is dot product of this vector with this vector will be mod of this vector into mod of this vector into cos of angle between them. And if the angle is 90 degree, cos of 90 degree is 0. I notice A bar is perpendicular to B bar cross C bar. So what will happen? The dot product of these two will be 0. So you understood that if any two vectors are collinear, when any two vectors are collinear with each other, then the scalar triple product value will be 0. I have considered both the cases and explained it to you. Now we go for the second case. See, what are we learning right now? We are learning that the scalar triple product of three vectors A bar, B bar, C bar is equal to 0 in following cases. Now we go for the next case, that is second case. See, the second case is when any two vectors are equal to each other. Now see students, this case when the two vectors are equal to each other is a special case of the earlier case. See, when the two vectors are collinear, what do you mean by collinear vectors? They are either in the same direction or in the opposite direction. Either in the same direction or in the opposite direction. What you saw that when the two vectors are in same direction or opposite direction, the angle between them is 0 or 180 degree. 0 or 180 degree, because of which sine theta is 0. And what happened? You got the final answer as 0. Okay. Now here what is happening? here you are getting two vectors are equal to each other. Now see, if any two vectors are equal to each other, what will happen? If the two vectors which are equal to each other are b bar cross c bar, if they are b bar and c bar, then you will get sign of 0, because if they are equal, definitely, if they are equal, definitely we are going to have the angle between them as 0, and sign of 0 will be 0. And then I will get a bar dot 0 bar, which is equal to 0. And if if we have two vectors equal, where we are not supposed to find the cross product, but it is like what we did here. Like if a bar is equal to b bar and we are going for b bar cross c bar, still what we notice is the length of a bar will be equal to b bar, but finally the b bar cross c bar we are getting, it will be perpendicular to a bar, and then again we are going to get 0. So remember students, this is when the two vectors are equal, is a special case of, it is a special case of earlier case. Okay. One more thing I would like to add in this is, see, when the two vectors are collinear, when the two vectors are collinear to each other, one vector is a scalar, it is a scalar multiple of other vector. Okay. So when you have b bar and c bar collinear to each other, when you have b bar and c bar collinear to each other, what will happen? This a bar, b bar, c bar will look like a bar, b bar, and m times c bar. Why? Because see, b bar and c bar are scalar, b bar and c bar are collinear to each other. So I can write, I'm sorry, I made a mistake, m times b bar. So since b bar and c bar are collinear to each other, I can definitely write c bar as a scalar multiple of b bar. I can definitely write c bar as scalar multiple of b bar. You know what I'm doing? I'm writing c bar is equal to mb bar. See, we know this right from the beginning. When two vectors are parallel to each other or collinear to each other, one vector can be expressed as a scalar multiple of other vector. Further, here I had a bar collinear to b bar. So see, when a bar is collinear to b bar, you could have written this as a bar, and see, you can have n a bar c bar. What is happening? Since a bar and b bar are collinear, I'm expressing this b bar as a scalar multiple of a bar. Okay, and this will also be 0. Remember students, this value is 0, this value is 0. Further, when the two vectors are equal to each other, it is like, it is like a bar, and b bar. What you will write? You will write the value as 0. If you have a bar, b bar, and b bar, the value is 0. Why? Because the two vectors, any two vectors from the three are equal to each other. Now we have the third case. The third case is, students, remember, the third case is when any one vector from three vectors is equal to 0. If any one vector from three vectors is equal to 0, that is, you have box product of a bar, b bar, c bar, and suppose out of these three any one is a 0 vector. Suppose you have 0 bar, b bar, and c bar. Suppose a bar is 0 bar. Definitely what will happen? Definitely, students, you know that the box product will be 0. Why? Because anyway you know that you calculate this by determinant. So if you have one of the vectors 0 bar, it means the coefficient of I cap, j cap, k cap all are 0. So you have 0, 0, 0, and here b1, b2, b3, c1, c2, c3. What will this be equal to? This will be definitely equal to 0. It will be definitely equal to 0. So this is also there. Now the fourth is we are writing the cases when the scalar triple product can be 0. The fourth one is when the three vectors a bar, b bar, c bar, a bar, b bar, c bar are coplanar vectors. They are coplanar vectors. Okay. Now, how do we have this case working? See, suppose I have a plane here. Let me have a plane here. So this is a plane. Now, in this plane, suppose I have three vectors, a bar, this is a bar, then the next vector I have is b bar, and then I have another vector as, say, I have it as c bar, right? So I have here a bar, b bar, and c bar. These three vectors are in one plane. You can understand they are in one single plane. They are in one single plane. See, this is the plane. See, this is the plane. They are in one single plane. See, they are in one single plane. Okay, fine. Now, what happens is I'm going for the scalar triple product of a bar, b bar, c bar. You all know when you go for this, what does it mean? It simply means, or suppose I'm going for c bar, a bar, b bar. I'm going for scalar triple product c bar, a bar, b bar. What does it mean? It simply means c bar dot a bar cross b bar, right? This is what it means. C bar, a bar, b bar will be c bar dot a bar cross b bar. Yes. So let me find out a bar cross b bar. So when I find a bar cross b bar, you all know I will start from a bar, go to b bar, okay, with my four fingers, and then the direction of the thumb will get me the direction of a bar cross b bar. So this is the direction of a bar cross b bar. Now, don't you see that this direction of a bar cross b bar, this is a bar cross b bar, and don't you see that it is perpendicular to the vectors b bar as well as a bar? Yes. Because of which this b bar cross a bar is perpendicular to both the vectors, because of which it is now perpendicular to the plane. And if it is perpendicular to the plane, remember a bar cross b bar is also perpendicular to c bar. Remember, students, it is also perpendicular to c bar. The direction of a bar cross b bar and the direction of c bar, they are perpendicular to each other. What is direction of c bar? Direction of c bar is this way. It is along the plane, in the plane, this way. Direction of c bar is along the plane this way, whereas direction of a bar cross b bar is perpendicular to the plane. You see this? These two directions are perpendicular to each other. So the angle between this vector and this vector is 90 degree. Now you know if it is 90 degree, then the dot product between these two vectors will be definitely 0. It will be 0. So you have c bar, a bar, b bar, box product as 0. Now you know if c bar, a bar, b bar is 0, then it will be 0 in all different orders, whether it is a bar, b bar, c bar, or it is b bar, a bar, c bar, all the way it will be, the value will be 0. So this is the fourth one that you have. The value of scalar triple product will be 0 when the value of scalar triple product will be 0 when the three vectors a bar, b bar, c bar are coplanar vectors. When the three vectors a bar, b bar, c bar are coplanar vectors. Now we have property number 4, and see, for property number 4, before I go for the property, I want to tell you that, see, students, you all know that dot product is commutative. It is commutative in nature. It is commutative. What does it mean? It means that if I have two vectors p bar and q bar, so p bar dot q bar is same as q bar dot p bar. So remember this property of dot product. Now I will come here. So suppose I'm writing a bar dot b bar cross c bar. What I'm writing? I'm writing a bar dot b bar cross c bar. Okay. Yes. You all know, students, that a bar dot b bar cross c bar, if there is cyclic change in the three vectors, then the value will remain same. If there is a cyclic change in the three vectors, then the value will remain same. That is, it is a bar, b bar, c bar. If I write this as, okay, how do you write a bar, b bar? How do you write a bar dot b bar cross c bar in box product? You write it as a bar, b bar, c bar. Okay, this is the way you write. Yes. Now I go for a cyclic change in the vectors. Okay, the change in the cyclic order. So this c bar is on the move to come to a bar, b bar will move to c bar, and a bar will move to b bar. So when it happens, what actually happens? See, the next scalar triple product, the next box product you get will be, here you will get c bar, this will become a bar, and this is b bar. Okay. Now this thing, see, as for this, you wrote a bar dot b bar cross c bar. As for this, you wrote a bar dot b bar cross c bar. What will you write for c bar, a bar, b bar? What will you write? You will write here c bar dot a bar cross b bar. What you will write? You will write c bar dot a bar cross b bar. You will write c bar dot a bar cross b bar. Now, as you know, students, that the dot product is commutative. What you know? You know that the dot product is commutative. So if I have c bar dot a bar cross b bar, can I write this as a bar cross b bar dot c bar? Can I write it this way? Definitely yes. You can always write it this way. This and this, they are equal. This is equal to this. This is equal to this. And remember, even this is equal to this. Why? Because you obtained this only by the change in cyclic order. So what do you now see? You see that, see, here you have a bar dot b bar cross c bar, which is equal to a bar cross c bar dot b bar. What are you noticing? You are noticing that here you have a bar dot b bar cross c bar, which is equal to a bar cross b bar dot c bar. So if I write it separately, it indicates something to us. See, a bar dot b bar cross c bar is this which I wrote. Now let me write the other one, which is equal to a bar cross b bar dot c bar.
So what I feel, look at the order. The orders are same. A bar, B bar, C bar, A bar, B bar, C bar. Only thing what has happened, the dot and the cross, they have interchanged each other. See, here you have dot first and cross second. Here cross is first and dot is second. So what you can say here, you can say that, you can say that in a scalar triple product, the dot and cross can be replaced. They can be interchanged. Okay, so this is the property number 4. I will write here. See, I will write here in a scalar triple product. In a scalar triple product, dot and cross, dot and cross can be interchanged. They can be interchanged. Remember that if you have A bar dot B bar cross C bar, you can write A bar cross B bar dot C bar. You can take cross here and dot here. It is still the same. Now I go for property number 5. See what is property number 5. In property number 5, I have several smaller properties which I am going to now write. So here see property number 5. See, if I have A bar, M B bar, C bar, it is equal to M times A bar, B bar, C bar. Remember, where M is a scalar, where M is a number, where M is a scalar. Remember that. Okay. So if you have A bar, M B ar and C bar scalar triple product, it is equal to M times A bar, B bar, C bar, C B. If you have A bar, M B bar and C bar, remember it is equal to M n times A bar, B bar and C bar. Okay, where M and N are scalars, where M and N are scalars. They are just numbers. What are they? They're just numbers. So enough for this video, students. In next video, I will give you the problems on scalar triple product. Thank you. I hope you followed everything.